In this lecture, we'll try to explain the more surprising orbits of extrasolar planets and discuss whether we need to modify our theory of solar system formation. The discovery of extrasolar planets gives us the opportunity to test our theory of solar system formation. Can our existing theory explain other planetary systems, or do we need to rethink things? The nebular theory is the model that describes how our solar system formed from a large cloud of interstellar gas and dust. In this model, planet formation is a natural consequence of the processes that accompanied the formation of our sun. If this theory is correct, then the same processes should accompany the births of other stars. Therefore, this theory clearly predicts the existence of other planetary systems. This is good because we are definitely seeing other planetary systems. But there are observations that are puzzling. In particular, the hot Jupiters. These are the large planets that have close-in or highly elliptical orbits. The nebular theory predicts that Jupiter-like planets should not form inside the frost line. Within the frost line, ices cannot condense, only metals and rock can. So these types of planets have triggered a re-examination of the nebular theory. So far, no compelling reason has been found to discard the basic theory. Instead, scientists think that the hot Jupiters were indeed born with circular orbits far from their stars, and that those that now have close-in or eccentric orbits underwent some sort of migration or ended where they are because of gravitational encounters with other objects. Planetary migration is the idea that hot Jupiters formed in the outer region of their star systems and then migrated inward. A possible cause of the migration has to do with waves in the planet-forming disk. Shortly after any star forms, there's a disk of material that surrounds it. It's from this disk that the planets form. A young hot Jupiter orbiting in this disk can bunch up the material, creating denser areas. These denser areas propagate like waves and exert a gravitational pull on the planet that causes it to migrate inward. Computer models confirm that waves in a nebula can cause young planets to spiral slowly toward their star. This wasn't significant in our own solar system because most of the material in the sun's disk cleared out earlier. This figure shows a simulation of waves created by a planet embedded in a disk of material surrounding its star. The material is getting bunched up and it's tugging on the planet, causing it to migrate inward. The highly eccentric orbits we've observed in some extrasolar planets can be explained with gravitational encounters. A close gravitational encounter between two massive planets can send one planet out of the star system entirely, while the other is flung inward into a highly elliptical orbit. Repeated encounters could cause significant migration. We haven't talked about resonances yet. Basically, an orbital resonance is the phenomenon of orbital periods falling into a simple mathematical relationship. For example, consider the moons of Jupiter. During the time Ganymede takes to complete one orbit of Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4 orbits. The 3 moons therefore line up periodically, and the gravitational tugs they exert on each other add up over time. Because these tugs are always in the same direction with each alignment, they tend to stretch out the orbits and make them slightly elliptical. The net effect is much like pushing a child on a swing. If timed properly, a series of small pushes can add up to a resonance that causes a child to swing quite high. For the 3 moons we just talked about, the resonance that makes their orbits elliptical comes from the small gravitational tugs that repeat at each alignment. The bottom line is that resonances can drive planets into eccentric orbits. It's just not clear whether resonances are common enough to explain the many planets that we found with the highly eccentric orbits. Based on our observations of planets around other stars, it's worth asking the question, do we need to modify our theory of solar system formation? If we're right about the role of planetary migration, then the basic tenets of the nebular theory still seem to hold. But there are some mysteries. If anything, we've shown that the nebular theory was incomplete and in need of a few new features. A much wider variety of solar system arrangements now seems possible. It's this variety that leads to yet another question. Given that we haven't discovered other solar systems that are quite like ours, does this mean that our solar system is of a rare type? Or does it mean that we haven't acquired enough data to see how common solar systems like ours really are? This question has implications for the search for life in the universe. Are planets like ours that support life common or rare? We'll address this question in greater detail towards the end of the semester. That's it for now. Take care. I'll talk to you soon.